Are there any questions? Oh, by the way, if someone is willing, and you guys want to, if someone's willing to find a mobile whiteboard, we'll have a class outside on Thursday. But you have to facilitate that happening. I'm not going to go tracking on a whiteboard. If someone can figure out how to do it, send me an email. We'll do it. I think it's going to be nice on Thursday. Anyway, all right. Okay, so good thing Martin showed up because he's the top card. He was got the first question. Are there any questions about stuff so far?
So I just want to make sure I'm thinking about this right. For gluons, we have to draw the arrow on it because even though a gluon is its own antiparticle, it's a different state.
Did I say gluons were their own antiparticles?
Well, aren't they?
No.
They're not? Then what's the antiparticle of the gluon?
So what is the antiparticle of any particle? What is how do you define the antiparticle, if you will? You
charge conjugated.
You charge conjugated, which basically means you reverse all internal quantum numbers. Like electric charge is what we tend to think of, but color charge as well.
Okay.
So if I have a gluon that's, I mean, I know the gluons are in these color octet states, so they're more complicated than what I'm about to write.
Yeah.
But if I had a gluon that was, red, blue bar, and I conjugate that, I'm going to get red bar blue.
Okay.
So this would be the anti-gluon to this gluon.
But in red bar blue, can it be just a gluon?
Can this be a gluon? Well, no, the gluon, so if, look at the list of octet states that I gave you last time. So we said that the gluons are one of those octet states. There's 8 of them. And so if you conjugate the colors in there, okay, you see what I'm saying?
Yeah. Okay.
You conjugate the colors, then the gluons turn into their anti-gluons. Now some of those states are symmetric, but some are not.
Okay.
But generally, to define an antiparticle, you change all of the internal quantum numbers.
Okay. So there's a separate octet of anti-gluons.
Yeah, exactly. The photon, however, carries no charge whatsoever. No weak charge, no color charge, no electromagnetic charge. Therefore, it's its own antiparticle.
Okay.
So in general, you can form different states out of those basis octet states, right?
Sure, that's just sort of a linearly independent set of
So would you, if you had some gluon, could it be a combination of those states, or is it always one of those? If you have a gluon that.
Well, when we draw, so we're going to draw pictures today, and I think you're going to get an idea of what gluon you should be considering in what context. So I think it's in the context of actually constructing the diagrams that this is going to make a lot more sense, which is what we're going to start right off the bat with. So that might help answer your question when we start drawing pictures. Well, actually, we're going to cheat. So, I mean, actually, it's interesting that you asked that very question because in truth, when we draw diagrams and we consider processes, we actually kind of cheat, and we don't use the octet states. We just use a piece, a color anti-color piece, because in truth, you'll understand why when I try and draw a diagram. You'll understand oh yeah, that would be hard if you actually used an octet state because it would look weird. I'll reiterate that point when I actually draw the diagram. Mark.
So the octet states that you gave us are just the conventional basis for.
Yeah.
Okay. Why'd they make it so complicated? I guess, because I mean, you can pick any basis, so I'm just curious as to why you would use one where they're in these weird sort of singlet or singlet-like states versus just isolated basis states that are less than 4 stable.
Well, I mean, you're working under a set of states which are transformed into each other under SU3 transformations, and why pick one basis over another? Off the top of my head, I don't have a good answer to it. I don't know if there's a simpler basis.
Okay.
But yeah. I don't know off the top of my head. There's a few thoughts going through my head, but I'd have to work them out, and we got too much to cover. Okay, see, these are good questions, but I think some of this will become clearer when we actually start going through some of this. So we're going to start by answering one of the questions. Why is the strong interaction not so? After all, we might say in the world of nucleons, which is where we typically encounter in terms of particles that exist every day, nucleons, and by nucleon I mean the constituents of the nucleus, so protons and neutrons. Those are the hadrons or quark bound states that we most frequently encounter in nature. We can create all these exotic things like pi mesons, et cetera, in colliders, but if we just look out in the universe, typically we only see neutrons and protons. So when we think about the interaction of neutrons and protons, and I know these are bound states of quarks, but I'm going to treat them like they are just single particles for the moment. If I collide two protons, then we know that this procedure can be mediated by an electromagnetic interaction by the exchange of a photon. Okay, but then you might say, well, if I could somehow mediate the interaction by the exchange of a gluon, then since the electromagnetic coupling, alpha electromagnetic, is stronger than the strong interaction coupling, these are both second order diagrams, this should actually play a more important role in the interactions between, for example, two protons than the electromagnetic interaction. So the first question we're going to ask is, why do we not observe that? Like, why aren't the strong interactions like really in our face? Okay. And I mean, you might say, well, they are. They hold the nucleus together. I'm saying if you just take two protons and hold them like here, they'll feel an electromagnetic interaction that will overpower any strong interaction between the two of them. Okay. When you get things bound in a nucleus, things get a little bit more complicated. Okay. And part of that has to do with the running of the couplings, et cetera, et cetera. But generally speaking, I mean, everything you learn in electromagnetism in physics 2, you thought about charged particles like two protons, you talked about the electromagnetic interaction. Why did you not have to take into account the strong interaction between them? Why was it effectively not important? Well, first of all, we have to be a little bit careful. This is all actually the result, or the truth of this story is that these are bound states of quarks. And so we should remind ourselves of that. In the electromagnetic case, it's not so important how we distinguish the set of quarks. Okay, I mean, we know that there's, for the proton, up, up, down, and we've got no neutrons in here, so it's up, up, down. But for this particular process, okay, the interaction is, you've got to be a little bit careful. So one way to sort of model this interaction is to say that this is three quarks, and two of them just go along for the ride. They're called spectator quarks. And then one of them, just maybe the down quark, you could pick any of the quarks to actually have this exchange. One of these quarks would exchange a gluon with maybe the up quark here. It doesn't matter which one you have it interact with. And even in this model, you might be tempted to say, okay, fine, we'll break it up into three quarks, and then this is actually the exchange between two of them of a photon. Okay. The quarks here are fractionally charged, so maybe that kind of mucks things up by a factor of a third or 2/3, depending on which quarks you pick to actually exchange the photon between. But nonetheless, that hasn't changed the argument that there's two vertices here, the strong coupling is bigger than the electromagnetic coupling. This seems like it should be a more important process. Here is the problem. This can't happen. And to understand why it can't happen, we actually have to go and follow the color. Okay? So first of all, this can definitely happen. If this is some charged quark, this is the same charged quark. Emission of a photon doesn't change anything. one of the nice properties of QED that makes it so simple. However, in the strong interactions, emission or absorption of gluons changes the color state. And it's in that changing of the color state that this interaction gets modified quite significantly. So if we tried to assign color, I'm going to blow this picture up a little bit. If we actually tried to assign color states to the quarks in this process, we might make an assignment like the following. So I'm going to be, it doesn't matter. So if I call this a red up quark, a green up quark, and a blue down quark, okay? Red, green, blue, why would I pick those colors?
It's colorless.
Yeah, because as we'll talk about in a few minutes, the hadrons, baryons or mesons, have to exist in colorless bound states, so that's always going to be a color anticolor or a combination of all three colors. So red, green, and blue works. And then let's just suppose that this is a red up quark, a green up quark, and a blue down quark here. Okay? Now, as these things come in and there's this event, clearly none of this changes. The only thing I have to figure out is there's an exchange of a gluon, what happens to the down quark from this proton and the up quark from this proton. And if we just, picked something, maybe we would say that the gluon carries the red away from this line, so we can draw the gluon as if it's moving up. And we can say that the gluon is carrying red away, and when it hits this vertex, it gives this red, but it has to take away the blue. So we would call this blue bar. So it's a bicolored gluon, as all gluons are, carries color and anticolor. And clearly, and Robin, this might relate to your question, if I had chosen instead to have this gluon propagate down, that means I would be using the antiparticle, which would be a red bar blue gluon, which would make sense because it would carry the blue away from here, give it to this guy, and cancel off the red. Okay? Of course, if I carry blue, or if I carry blue away from here, the blue goes away, but what happens if I carry anti-red away? This is left with red. Okay? So at the end of the day, no matter which gluon I pick, this is going to become a red, and this is going to become Martin.
There should be not just blue.
A blue up. A blue upward. Okay. Right? Blue upward. Blue up. Blade loaded up. What's the problem? It's not colorless. Okay. States coming out are not colorless. They're colorful. Even though we started with colorless. Now you might say, well, that's just one example, Flournoy. I could have probably maybe made different color assignments and, got this to be something else. And then again, you cheated because you used a gluon that wasn't one of the octets. So, what the hell are you doing? First of all, in all the strong interaction processes that we're going to draw, we're always going to draw a gluon exchange in terms of just a simple, color anticolor combination. And you might oppose that and say you should work with those octet combinations, but then we should go back and we should say, well, actually, maybe we should be working with more complicated linear combinations to describe the baryons and the mesons as well. So if you do it all together, it's consistent, but you can make the arguments based on just working with two color gluons and then single color assignments for these. The truth is that working with the superposition will net you the same results, because you're going to end up summing over everything at the end of your calculation anyway. Yes?
I haven't written down that octet, but can't you make that particular gluon from some linear combination of that octet?
Sure, you can.
Okay.
You can.
So I mean, isn't that a valid?
Yeah, but yes, it is a valid state, but in principle, you might say, could we just work in terms of those octets, and they would be complicated, because you'd have to be linearly superposing several of these diagrams, and it would look really weird. So we're gonna work with these linear combinations, just for simplicity. Now, you could try other combinations, but the truth is no matter what combinations you try, you're gonna find that you're always ending up with colorful states coming out. Unless you allow yourself to do this slightly differently. You can get this to work with the following process. Which is marginally more complicated, but not too bad.
Do you need color on those states?
I'm not even going to bother assigning color. I'll let you do that on your own if you'd like to figure it out. I'm just going to show you what the process looks like. So, again, these are 2 protons. And we're going to start with a gluon exchange between these guys. And then this guy is going to come out as one of my spectator, one of my final proton quarks. And then we're going to have this guy exchange a gluon with a virtual quark. This guy is going to give me a virtual quark. And my lines are crossing in a weird way. I'm not sure why they're crossing that way. So look at my paper, right? Okay, so we're going to have a line come down here, line come down here. That's going to be my down quark. This guy is going to hit over here and exchange with this line to give me a quark. I have too many lines here. What is going on with my lines?
Perfect.
I'm missing, I think it might be this guy. Yeah. My picture's drawn wrong in my notes. I should have double checked that. Okay.
There's one vertex in there that doesn't make any sense.
Is there a disallowed vertex in there?
Yeah, there's a, on the top up quark, on the bottom proton, the first vertex.
This one?
Down. Out.
Is that the one?
That's not a vertex.
Oh, I see.
That's just a line over, I mean, you could do the little jump over kind of things. Mark?
So with regard to that first diagram, why can't you say that up quark on the bottom is like up blue and it exchanges a blue anti-blue with the down blue?
So you could, and this is where the details of the linear combinations get kind of murky, but effectively to realize that interaction would be making use of this 9th gluon, the completely trivial. It transforms trivially under SU3, and that's the one that doesn't exist.
Okay.
In this context, that would look like trying to send a blue anti-blue, but really that state is that linear combination of the triple of color anti-color states, but it doesn't exist, the particle that you need. Okay, so I'm not even going to bother with the labels of the colors, but you can go home and you can pick labels of colors, and you will find that you can actually pick certain bicolor assignments for the gluons, where this thing will actually start with colorless protons and give you out colorless protons. But most importantly, and this isn't obvious, you actually would want to fill in the details, okay? But most importantly, this is the lowest order contribution. Well, what order is this? It's 8th order, okay? So we automatically know from the Feynman rules that this is going to be accompanied by a factor of alpha strong to the 8th. You get a factor for every vertex. There's 8 vertices. Okay? So the electromagnetic interaction will carry a factor of the electromagnetic coupling squared, but this rather indirect process, strong interaction between nucleons, okay, is only going to come in at 8th order. So it's when you actually start comparing the relative importance of certain contributions to physics, you can't just take one result and say that's always the answer. Like the bigger coupling is more important, or the weaker coupling is less important. You've also got to couple that with, well, at what order are things coming in? You can't always say that just because two things are at the same order, that they have the same size effects, because the couplings might be different. Or, as we learned last time, the mass of the mediator might be different, and that can make things comparatively weaker, as we see in the weak interactions. Okay, Martin?
The energies we're looking at, how much bigger is the strong interaction? Because it might be that this is still larger, or even comparable. Right?
Yeah, so I wish I had I don't have, do you have Griffiths?
Yeah.
See if he gets a value for the strong interaction coupling at basically 0 momentum transfer. If he lists the value at all, it'll be the 0 momentum transfer value. So let me see. So we know this guy is 1 over 137. Did you get value? Okay, well, when Patrick finds a value, we'll let you know. But it's sufficient that at 8th order, it's still incredibly weak. It's not that much bigger. I mean, yeah, when Patrick gets a value, you'll be convinced. I just don't know off the top of my head. Other questions? Okay. So now we're going to turn to the second question we thought about addressing, which was how do we argue that quarks have to appear in bound states? And this is where we're going to get, so we could argue this just by drawing diagrams and following color. So that's kind of, you could teach that to a 3rd grader with sufficient background material. So we'll fill this in when Patrick finds the value of alpha S. Or if somebody has a phone and Wikipedia, they can maybe just Wikipedia strong coupling at 0 momentum transfer. And I know when I say strong coupling at 0 momentum transfer, that might not mean something to you. It will after Thursday's lecture. Have a value?
I got 1. This is from hyperphysics. But it says 1 over 137 for
You got 1?
1. Alpha strong is 1.
The relative.
One what?
Yeah.
They're dimensionless numbers, so if it's 1, it's 1.
So they're all measured with respect to, I think, the strong force. Like the 1 over 137, I think, is relative to the strong force. Yeah.
At a certain energy though.
Right, but the energy was
Right, that relative
then
values
not
aren't
the
converted
8
from
to
here.
1.
Trying to raise those powers.
I can give it to you as a function of energy.
Okay, give it. No, don't give it to me. Yeah, I'll think about it, Martin. I don't have the answer off the top of my head. I don't. If you're setting everything relative to the Strong's coupling, but these are all dimensionless numbers, I'm not actually sure how you do that scaling. Like I understand how you can do scaling if you have dimensionful numbers to work with, but yeah, I'm not sure. I'm not sure.
So why is it that when you get the protons, like neutrons, close enough that the strong interaction then overpowers the electromagnetic?
Well, so it's a combination of a couple of things. First of all, you're never going to get the strong interaction between two protons to overcome the electromagnetic repulsion. Otherwise, you'd have bound states of two protons. So to get things stable, you actually have to throw neutrons into the mix. And the nice thing about neutrons is they don't contribute to the electromagnetic exchange, but they do contribute to the strong interaction exchange. So that's why our nuclei tend to be built up of protons and neutrons. And if you actually look at nuclear stability, it's very sensitive to how many neutrons and protons you have to add in more and more neutrons to get it to be stable.
Are neutrons stable?
But the other thing, say it again?
Are neutrons stable on their own?
No, outside of a nucleus, the neutron will decay. It can decay. I mean, it's heavier than the proton, and through a weak interaction process, the neutron's quark substructure can decay to the proton substructure with an electron and an anti-electron neutrino. So that's a process which I might have gotten to if we had any hope of getting to the weak interactions today, but that's clearly not going to happen. So we're just going to go at our pace. But yeah, the neutron will decay. The other thing is when you have things in close proximity, then you're talking about a high energy state versus a low energy state, and then you have to take into account the running of the couplings. So is when I'm drawing these diagrams and when I said take two protons this far apart, I was secretly saying where it's basically at zero momentum transfer. This is kind of the lowest value of these quantities, or this is the most screened value of these quantities. And if you start putting things together at nuclear distances, then you actually have to start taking into account, well, how does the strong coupling change as you actually change the energy scale? And that's something we really won't understand until Thursday when we talk about renormalization. Okay, so so I need to get through at least the Meson example. So we're going to start our analysis of why are things bound with the simpler case of mesons. That's two quarks, a quark and an antiquark. And I'll, if time permits, say something about baryons, but I'll at least tell you why it's a little bit more complicated. So for mesons, we know that these are always a combination of a quark and an antiquark. They don't have to be the same quark. You can have an up quark and a down quark, or you can have an up quark and an anti-up quark. But they have to come in, we observe them in colorless combinations. So whatever quark this is, if this is red, this has to be anti-red. Okay. So the way we're going to argue that that is required is as follows. What we're going to find is if we sort of study the interaction between the two quarks in the meson, what we can extract, and we'll make this argument in just a moment, is the following. If they're in a colorless combination, then the force between them is attractive. However, if they're in a colorful combination, so if I made this one red but I made this one anti-blue, then the force between them is actually repulsive. Okay. Now, you might say, well, that just means that if you put two quarks like this, they would actually move apart, and then you'd have free quarks, and life would be good. Right. Well, what happens when these quarks fly apart is a separate part of the story, which we'll try and touch on. But for now, what I want to focus on is the simple idea that if you're making a bound state, your force better be attractive. If take two electrons and try to make a bound state out of them, how's that going to work?
A lot.
Right? Say it again.
A lot better.
Well, I mean, how much energy do you need? Can you ever get a repulsive force to create a bound state? I mean, if that's the only force you're talking about, no. Okay, so we have to have an attractive force to have a bound state. So let's actually see if we can conclude that the colorless gives us an attractive force, whereas the colorful gives us a repulsive force.
So here you're exploring if one were colorless or colorful. What about, are you taking for granted that one has to be a particle and the other an antiquark? One has to be a quark and the other an antiquark? Like what if they were two quarks or two antiquarks.
So that wouldn't actually change anything, because if they were two quarks, there's no way they can be colorless.
Oh, okay.
So that would still be colorful.
So that also covers that.
Yes. Okay, so here we go. I mean, this, I'm saying a lot of words, but now we're going to do a calculation. Okay, and we're going to use Feynman diagrams and evaluate amplitudes. Okay, so here we go. So we need to sort of draw a process that describes this, and this is it's a bit of a cheat, but
It starts to be a semantic,
it's a bit of a cheat, but here we go. At leading order, I can draw this actually as a scattering process. So I'm going to pick, for example, an up quark and a down quark as my constituents. Yeah. I'm going to have an up quark coming in, an anti-down coming out, and then we can just fill this in with strong interaction vertices. And so at lowest order, I have a gluon exchange. So I'm going to label my momenta 2, 4, 3. Call this Q, and I'm going to have my gluon going up. Okay. All right. So all I'm interested in is the interaction between the two particles that are, I think, I'm making up a bound state. And I just want to investigate whether it's attractive or repulsive. Now, looking at this picture, when we draw Feynman diagrams, they're always kind of suggestive, right? It's like, oh, this is repulsive because they came together and they flew apart. Okay, that is not something that's indicated in a Feynman diagram, as much as you might like to think it is. Because after all, if we made this an electron and it's an anti-electron and an electron, we know that electromagnetically those are attracted to each other, but we would draw the same damn picture. Okay, so the kink in the arrows and the directionality is not supposed to indicate attraction or repulsion. All right, that's not indicated in Feynman diagrams. It's just there's an interaction between these particles via the exchange of something. We have to dig a little deeper to figure out whether it was attractive or repulsive. Okay, so how are we going to figure that out? Well, we're going to calculate the amplitude, M. And to calculate the amplitude of M, we're going to utilize the Feynman rules for QCD, which we talked about last time. Okay? So I'm going to just go ahead and write down the final expression, and we'll go back and make sure that everything makes sense. And it might be worthwhile for you to peek back at the Feynman rules for QCD, so that when we go over this, say, yeah, I would have expected to see that. Or, no, I have no idea what formula is writing on the board. I've never seen that before in my entire life. Okay. So let's go through this a little bit at a time. First of all, you'll notice a spinner sandwich. We start with a U bar 3 going out, so we're coming in this line. So we've got the U bar 3, we've got the color factor for that line. Okay, remember our external states have to be labeled with a color designation as well, so that's what these C's are. We hit a vertex, so we get a vertex factor. Again, the vertex factor looks a lot like QED, except for we have this matrix lambda, which is connecting the color space to the gluon space. And then we come out this incoming quark line, so we get another factor of U, this time with its own color factor. I just conveniently placed the propagator for the gluon in square brackets here. Again, looks a lot like a photon propagator with the exception of these this color indexed matrix. And then again, coming up here, we come in on the V2, or the anti-particle coming in, hit a vertex, and then we go out the outgoing anti-particle, finishing up with a V4C4. Okay, so I just applied the Feynman rules. You would crank out or you would throw down delta functions, integral over dq, okay? But then you could use the delta functions to do the integral over q, and then erase the overall momentum conserving delta function, multiply by I, and that's where this m came from. Yes?
The particles that go in are going to have different color charges than the particles that come out, because you have this gluon exchange.
Yeah.
So how can we call this a scattering if it's not the same going in as going out?
So the word scattering in high energy physics is a very loosely, so the word scattering can literally mean like,
Okay.
you can take two particles and smash them together and get a gazillion things out, and we'd call that scattering. Okay, the things that come out don't have to be the things that come in. For simplicity, we restrict ourselves to two types of thing. Scattering, where we usually just think of two things interacting, and then any amount of stuff can come out the same or different or whatever. Or decays, where one thing goes in and then any amount of stuff comes out. You could try and do three things scattering, but then it becomes really tricky to do experimentally. So, right,
Okay.
you gotta get all within close enough proximity to actually have interaction. So yeah, it's sort of one of these generalized scattering events. You know, it's certainly not what you get when you scatter satellites off of planets gravitationally, unless, of course, you know, the satellite actually hit the Earth and broke the chunk off. And, yeah.
So why is there still a Q in that term?
Yeah, so we would have integrated it. This Q, we already know. I mean, we can look at the picture and tell what Q is going to be, right? I didn't put it in, but what would Q be? Could you relate Q to the momenta in the picture?
Yes.
Yeah, what would it be?
Exchange momentum.
So how about P1 minus P3? Or you could express it in terms of 2 and 4. There's different ways to express it. So a lot of times, if we're not actually going to evaluate this, I mean, you'd stick it into the golden rule and integrate it, but I'm not really interested in doing that. So, right, this Q is secretly, you know, P1 minus P3, if you will. I'm not worried about evaluating it in that way.
So since we can choose it to be in terms of P1 and P3 or P2 and P4, is that just something you choose based on your experiment? Like you would know?
No, it literally so this is not the answer, right? This is not a number. This is something which we would eventually stick into the golden rule, which itself is going to integrate over these things, the outgoing momentum. And then the only thing experimentally that you specify are these incoming momentum.
Well, I guess why did we choose P1 minus P3 instead of the 2 and 4? Like, is there some reason you would
It's not going to affect the final answer, is what I'm saying. Like, you could use either one, and it won't affect the final answer, because part of the golden rule is going to go back and restore overall energy momentum conservation. So it knows at the end of the day that Q is going to be what comes out of here and what goes into here. So it's literally just an arbitrary step right now that'll lead you to the same answer no matter which way you go. Okay, so any other questions about this? So literally this is just applying the final rules for QCD. Nothing strange in having written that down. But now I'm going to do something which is going to seem a little devious. I'm going to notice, so I'm going to play a little game. Martin has already been beaten up. Monica's not here. He's here. Eric. There you are. You have darker hair in the picture. That's what. You guys look a little different than you did at the beginning of the semester. So you really throw me when I look at the picture, then I look for you in the room.
That was my picture for GR too, so that's like a
That's
year plus.
true. Yeah. Like I don't think you'd hit puberty in this picture. So. That's me. That's me. I'm going to point to things in this expression, and I want you to tell me in what space they are not trivial. Okay. Or in what spaces they're not trivial. So this.
Spin space, color space. That would be spin space and space time and color space. Oh, just the lambda would be spin and color.
Yeah.
And that would be spin and space time. Spin, color.
Okay.
That would be That I don't, oh, spin space. No?
Color space.
Color space, okay.
It's color space. Or, sorry, no, it's gluon space.
What does that mean?
The alpha, remember the lambdas secretly carry an ij.
Okay.
So these label spin, sorry, these are color indices, and this is the gluon state.
Oh, okay.
And then this is just linking up two gluons.
Gotcha.
Okay, so I'm not going to go through the rest of it.
Sorry, can you say what the lambda isn't trivial in?
So the lambdas are the generators of SU3. There are 8 of them. That's why we have this index. It tells you which of the generators you're working with. And then as generators of SU3, they are 3 by 3 matrices which act on color vectors. So the ij are the matrix indices.
Okay.
So they're non-trivial in sort of gluon space, this 8-dimensional gluon space, but also in color space. Okay. And that's kind of analogous to the gammas, which are a vector in space-time, but they're matrices in spin space. We just don't ever write the spin indices. Okay, now in all of that, what I want to point out is this is only non-trivial in color space, which means I can move it past anything I want, except for things which are non-trivial in color space. This is non-trivial in color and gluon space, so I can move it past spinners and spin matrices as much as I want without worry. In fact, what I can do is I can take all of this and I can extricate the following. All right? And this is perfectly allowed because all I did was took all of the color and gluon factors and just moved them past all of the spin and space-time stuff because one is trivial in the space that the other one is non-trivial in. Okay? Now I preserve the order of everything as I kind of move them apart. But here's the key thing. This guy right here is the same thing you would get if you calculated M from the scattering of an electron with an or an electron with an anti-muon. Yeah.
That would have the E and M coupling, not the strong coupling.
Right, so
you
the
just
only
have
thing
to
that would
be a
change is
different
the
factor.
size of this number, but otherwise,
Yeah.
and that's just a size difference. Martin?
Question, when you have your two lambda alphas, is that because you use the delta to raise?
Yeah. So we're being a little bit, okay, yeah, I'm being a little bit sloppy, but this is the convention in the literature, unfortunately. So the metric in gluon space is trivial, so we don't necessarily need to worry about distinguishing between upper and lower indices like we do with, for example, space-time or any space where the metric is non-trivial. So you might have objected, GR people should have objected, you didn't, you lazy pieces of crap, that, hey, Flarler, wait a minute, you've got repeated indices and they're both upper. Normally we say with the repeated, one has to be up, one has to be down. So, if I wanted to be a little careful about it, I might write that.
And then the next one would be.
Yeah, and then one of these would be up and one of them down. But that's sort of overkill because there's no reason to distinguish up and down for these indices because the metric is trivial anyway.
Do you still sum over them?
Yeah, you sum up. Yeah, we're going to calculate that factor in just a minute. But here's the bottom line. as interesting and abstract as this expression might be, at the end of the day, it comes down to a color factor multiplying a familiar result. In fact, this is what we're going to use to give us the final conclusion of whether or not this is an attractive or repulsive interaction, because after all, what kind of interaction is this?
Attractive.
It's an attractive interaction.
Attractive.
I find that repulsive.
You would call it repulsive? So this is a lepton and an anti-lepton, so they have opposite charges, so this is an attractive electromagnetic interaction.
I'm still repulsive.
So if this overall color factor maintains the sign of this overall amplitude, then it's going to be an overall attractive interaction. However, if this color factor turns out to contribute a negative sign, it can give a numerical shift as well, but if it changes the sign, then it's going to turn into a repulsive interaction. So the only thing we have to do to figure out whether the interaction between these two quarks is attractive or repulsive is to calculate this color factor, in particular its sign. Okay, now we're going to do that explicitly.
Why does the sign of M determine whether something is attractive or repulsive?
Yeah, so there's a way that you can actually extricate from these amplitudes the effective potential associated with the interaction. And that's actually where we tend to get these ideas of whether this is attractive or repulsive.
Okay.
So we're not going to go through the machinery of that. So at a certain level, you're going to have to take my word for it.
Okay.
But the book does a pretty decent job when it studies bound states of extracting this effective potential from the amplitude. But it's definitely controlled by the sign.
You don't gather that from Fermi's golden rule, right? Because that only cares about the square modulus?
Right.
Okay. So is that a different analysis altogether? Okay.
Yep. I mean, this is not a true scattering event, right? These quarks are actually bound. So, you know, we're cheating by even drawing this as a scattering event. There are reasons why it's actually okay to think of it as a scattering event, but that again ties into this renormalization story and how the QCD coupling actually changes with energy scale. So I wish I had just taught you renormalization the first day of class. Might have been a little hard, but you can have done it. Okay, so our next task is to calculate this color factor. We got to figure out what this thing is, all right? So with that in mind, I'm going to erase all of this good stuff and just focus on the color factor. So let us now assume, for simplicity, a set of color assignments. And let's start with a colorful example. So what I have to do is I now have to label all of these quarks with colors. And I'm going to just imagine that this guy is a blue. It's actually anti-blue. I'm going to say that this guy is red, this guy is red, and this guy is blue. I clearly am going to have to then cheat and use the gluon that doesn't exist, but we could pick different color assignments, et cetera, et cetera. Just for now, let me just pick these color assignments and calculate the color factor. And then we could argue about whether this is a consistent diagram, et cetera, beyond that. But so just to have some color labels, let me pick blue and red here. And then my color factors would be then C1 I'm taking to be in the red state. So we said that this would be 1, 0, 0. Remember the C's are 3-component vectors. C2 is blue coming in. So we said that the blue color state vector would be 0, 1, 0. C3 is again red. and C4, 0, 1, 0.
Do you have to carry a negative sign in or anything for the fact that it's an anti-blue?
No. So the fact that it's anti-blue is going to be reflected in the fact that it is going to be, depending on where it is, Hermitian conjugated or not. So the fact that it was associated with an antiparticle went along with the external spin state label, which, so the U's, the V's, the U bars, the V bars, and then depending on which side of the spinner sandwich they sat on, the associated color factor was either Hermitian conjugated or not. So this expression actually knows which of these C's is associated with an antiparticle and which isn't.
Okay.
It's built into the expression. You don't have to further specify it here.
Okay, that makes sense.
I mean, to write down M, we had to specify what was particles and antiparticles, and then it actually informed the structure of what we wrote down. So you don't want to be redundant and try and go back and re-specify it.
Right.
Okay, so let's calculate the color factor F. So I've got 1/4. Factor of 1/4 clearly isn't going to change anything. If I take C3 and I dagger it, can you guys dagger C3 in your head?
That's hard.
You can't do it? All right, well, I'll show you. So dagger means you complex conjugate, and everything here is real. That means there's no imaginary, no, I'm not talking about dragons. There's no imaginary. You guys said you couldn't do this. No, okay, I know you guys can do this.
I like the dragon stories.
Okay, C1, boom. Oh, Claudia, you'll be fine. You guys can initially congregate that guy. C4. Okay. Now, though, we need the lambdas. Anybody know what the lambdas are?
Just the identity matrix, just
Just throw in some identities.
Yeah, that's good.
So I didn't give you the lambdas in the last lecture, did I? I didn't actually write them down.
They were in the homework.
They were in the homework. So that homework I gave you when you were looking at the group SU3, I gave you a set of 8 lambda matrices. They're all these 3x3 matrices, and they're mostly 1s and 0s, but there's some i's, and then one of them, the lambda 8's got a root 3 and a 2 in it for some strange reason. But they basically are reflective of those combinations that I wrote down in the octet states. But anyway, the lambdas are a set of 8 matrices. That's all I'm going to say. They're written in the notes. You can look at them online. They were given to you in that homework assignment where you actually worked with them. But there are 8 of them. And we're summing over the index alpha. So we're literally going to take this expression, plug in lambda 1, evaluate this matrix product, plug in 2 and 2, evaluate the matrix product, 3 and 3, evaluate the matrix product, do it for all 8 lambdas, and then add the results together.
What do we get?
Glad you asked.
Since it's associative.
I knew it.
Matrix location is associative.
So
you have all that zero.
Yeah, that's just a tedious thing. I mean, look, you guys, I mean, I know if you can conjugate this, you could do this. You're literally plugging in a 3x3 matrix here, it's the same 3x3 matrix here, doing matrix multiplication, that'll give you a number, and then you're doing it 7 more times, okay? And then you add up the results and you get minus 1/6.
So it's repulsive.
So it's repulsive, okay? Now you might say, okay, fine, one colorful state is repulsive.
Check all of them.
You can check all of them and you'll always come back to a negative color factor. I'm clearly not going to do every case. I'm too lazy to plug in the lambdas. Okay? So how would we then do this calculation if we were considering a colorless state, or yeah, a colorless state? Well, just to give you an idea of how complicated things can get, because some of you are really bothered about, not doing this honestly, I'll just show you how this might work. So let's suppose that this was red, anti-red. Okay. So this is clearly colorless. It's a red and an anti-red. In truth, though, what we should be doing is yeah, so the gluon that is going to be exchanged in this, okay, it's a, this is just awful. Okay, here we go. Oh, no, sorry.
Different.
I'm not going to use this. I'm going to use the actual invariant state, so I just want to give you an idea of how bad it can be. Okay, so that's the actual colorless, or the SU3 invariant combination of color states. So this is the state that our incoming up and down quark are in. It's not just color anti-color, it's a linear combination of all three. Okay. This is what we would have called the ninth gluon state if it existed, but it doesn't. But this is a colorless combination of color and anti-color, so this is the state that this meson has to be in. Now, if we actually wanted to do the calculation over here, clearly assigning color vectors to these is going to be complicated because the color vector of this quark, okay, is not just a color vector times a color vector, it's these combinations all added together. So to give you an idea of how bad it's going to be, if I take C1 and C2, the two color factors for the incoming quarks, then to construct that beast, I'm going to have 1 over root 3. Again, red bar, so 1, 0, 0, 1, 0, 0. Okay.
Let's pretend one of them's transposed.
Okay. So I can't just write down C1 by itself, right? These are entangled, if you will. Okay. So the only thing I can do is consider C1, C2 as a combination together. And then I can decompose it into these three color anti-color states.
But we need to jam a lambda in the middle of this.
You guys sound like heads are ready to explode. Just want to give you some indication of why you know. So that's the same set of color factors because the outgoing state is also colorless. All right, so if I want to evaluate the color factor, I'm not changing anything over there. Yeah. Okay, so now you can see that if I'm going to have to evaluate C1 and C2, all right, I've got these two things right next to each other. So I can evaluate this guy, throw in the matrices here, and then I can evaluate these two. Okay? At the end of the day, this is just, I'm not even going to write all this down, it's hideous. But you're going to end up with something that looks like the following, just to give you an idea.
Why did you just write 1 over 3? To make it look worse.
Well, the one over the first one over here is trivial.
So yeah, the other one's trivial at root space.
Yeah.
No. Root 3 count.
Just a quick question on the like C1, C2, or C3, C4. You have two column vectors together. Is that supposed to be like an outer product, or does that not matter? So it's like a 3 by 3 matrix for the color. Right. Okay.
So, I'm only showing this to you because I want you to realize if you actually sit and work with these linear superpositions, things get immensely complicated very quickly, all right? But at the end of the day, this is just going to be a number. And it turns out that actually if you massage this expression, it simplifies to that bad boy. Yeah, Jacob.
I don't see how you got any of that middle step.
That's fine.
Yeah, that's fine. That's fine.
I don't like not seeing that.
Well,
You have like 4 lambda alpha matrices in there.
oh, there's more than 4.
More
See
than
the dot, dot, dot?
Just keep going with the lambda
Yeah,
alpha.
yeah. I mean, so what am I doing? I'm taking basically this guy and this guy and this guy, and then this guy and this guy. And then I'm taking these and I'm combining them with the next step here to create this factor. So I'm looking at all these cross terms.
Okay, I see now. I gotcha.
I mean, think about this. A product of 2 of these is 3 terms added together, and then a product of 2 of these is 3 terms added together, and then they're both being multiplied together.
So is this the simplest case for a meson?
It's the only case. It is the only case. So this is the only colorless state. Is this red bar plus blue bar plus green bar times 1 over root 3. Okay. So at a certain level, it's worthwhile to actually see that it's complicated, but it is the only one to check. It is the only colorless combination. For the colorful combinations, there were many different ones. Okay, we could pick a particularly simple one and we can kind of work it out, but you could also check all the other ones. But this is the only colorless one, so it's worthwhile to actually
Why
see.
do the different particles' color states have to be entangled like this? Why couldn't it just be red bar and then?
Okay, yeah. So this goes back to that issue that we talked about last time, which is it's kind of bad language. But when I say colorless, what I actually mean is SU3 invariant.
Okay, and this is
the only SU3 invariant bicolor combination. Okay, because if I take red bar, I can do an SU3 transformation on it that will actually change it to something different than red bar.
Yeah. Okay.
Okay, but if I do any SU3 transformation on this, it always comes back to itself. We like to call that colorless, but really we should call it SU3 invariant. Okay. All right, so the details of this are not what's important. It is complicated. And again, just to kind of illustrate why sometimes in these QCD calculations we kind of cheat and just pick simple scenarios for color assignments. But again, at the end of the day, this thing is just a number because the lambdas are just matrices. And in fact, this is a combination that completely sums over the color indices of those matrices. And in fact corresponds to tracing over the product. So if you're confused about how that works out, if I had those index assignments, this would be matrix multiplication that would leave me with a matrix IK. But if I turn around and make the last index the same as the first index, then that's tracing over the result of the matrix product. Okay? So at this point, this is something I could send you home to do. Take the 8 lambdas, multiply them together, or multiply them by themselves, add the result, right? I do lambda 1, 1, or I do lambda 1 plus lambda 2 plus lambda 3 plus. They're just matrices. You do that, you add them together, you get a matrix. And then you trace it. And the trace is straightforward because the metric in this space is trivial, so you just add the diagonals. Okay? And you'll get a number. Yes. And that number turns out to be 4/3. I know, it's deep. But what's important is
greater than 1.
It's positive. Okay? It's positive. Now, another reason, and sadly this is a way to think about it, another reason why we couldn't have picked red bar to do this, I mean, you might have wished, Flournoy, why did you pick this god-awful linear combination to work with? If you had picked just red bar, it would have come out negative. Because red bar is non-trivial under SU3. And I know we would think of it as colorless, but it's non-trivial. The only way to get the positive answer is in this complicated scenario. It is the only combination that gives you a positive number for the color factor.
So then for baryons, there's multiple different.
We've got time. Okay. So,
Do we have time?
yeah. No, we don't, but yeah, time. Yeah, either one of you.
So like, why make a distinction of like having like a baryon, one of those two quarks, like this is a red baryon or anti-red. Why make that distinction when they're like just a linear superposition of all those colors? I'm just trying to like,
So these are mesons.
find that.
Okay, well, I just want to make sure if you were meant to talk about baryons.
Oh, yeah.
These are mesons. So what's your question now using meson?
So like, you chose like at first that like the simple one, so like it was a red anti-red, but we have to use. So why make the distinction? Why make a distinction like what color of the quarks are coming in? I guess I'm not really quite understanding. Like,
So you can be really sloppy in what color assignments you pick and make it be colorful. Even if it's not technically one of the octets, right? If it's not one of the octet states, it's a combination of the octet states, but it's still colorful. So for the colorful state, I could just pick anything I want. So I can just work with a simple color assignment and crank it out. But if I truly want a colorless SU3 invariant combination, this is the only thing I'm allowed to work with because there's only one of them. I can't make a linear combination of this with itself. It would be very interesting. Good. So I have to work with this color assignment, which unfortunately is more complicated than how the color vectors work out.
This is the only one.
So like your double, can you get 0? And if you can, does 0 mean anything, or is that just like?
I don't believe you could get 0.
That a cross section is 0, so they wouldn't interact.
Yeah.
It would just mean that.
Yeah, but I don't, actually, well, yeah, you,
0 and.
actually, maybe one way to get 0, I don't know off the top of my head, but if I were to make an educated guess, if you actually wrote down a process and then tried to make color assignments that were inconsistent with color conservation, because remember, this is just blind. It doesn't really, this is not really, you're not writing this down saying the gluon has this color. Okay, you're just saying I'm going to fix the colors of the incoming and outgoing quarks. And if you tried to make an assignment which was inconsistent with color conservation and just calculated this number, I'm guessing you'd get 0. But I'm not 100% sure. I would think that would be the case. Something's got to enforce color conservation in these calculations. Because that interaction can't happen. Like the strong interactions can start in color. Okay. It's kind of like if you tried to write down the electromagnetic. It's kind of like if you tried to write down M, the amplitude for the electromagnetic scattering of an electron and a neutrino. You could write it down, but the answer is going to be 0.
Okay, that makes sense.
Okay. All right. Okay, so baryons. Any other questions about this? I'm not sure even how much detail Griffiths goes into in this particular calculation. Patrick, how much detail does Griffiths go into in this?
I'm not sure.
In the colorless.
That part.
Yeah, he might actually write all this out in more detail. I'm not sure, but
I wouldn't think he would. I think he would leave it up to the reader to do it.
Yeah. I think it's pretty terrible, but, okay, so to kind of, in our last few minutes, and I, at some level, lament not getting to talk about the weak interactions, but they're just awful. They're really terrible. In the last few minutes, let's talk a little bit about oh my God, these are so awful. Yeah, you know what? I don't think I even want to get into there. So the problem with baryons is baryons. If we started to construct the process, okay, then we have to be really careful because in the Meson case, we were just comparing two particles interacting. So we had two particles coming in, two particles going out. But a baryon is a combination of three quarks. So if we drew a Feynman diagram associated with the process that's kind of talking about the inner quark potential, you have three particles coming in, which we already think is, wait, we haven't considered that, and three particles coming out. Okay. Now you could calculate M. How you would ever work with a golden rule associated with this is absentee, because we don't have a golden rule for something like this. But at any rate, it gets even more complicated because you might actually find that for two of the quarks, you might get an attractive interaction, and then you might say, oh, you know, based on those color assignments, this is a quark bound state. But then it might turn out that between two other quarks, you get a repulsive interaction. So there's a lot of, I mean, these are interacting on a quark by quark basis. They're, you know, pairs of quarks are interacting. There's no 3-point quark vertex interaction. It's always two quarks at a time, exchanging gluons. So it becomes a much more complicated beast, yeah, I think I'm going to leave this to the notes. Because assigning the color states themselves becomes a much more complicated procedure because we have, you know, three quarks instead of two. So even exploring color full combinations is more complicated. But at the end of the day, we find the same result. You know, essentially that there's one unique SU3 invariant set of color assignments for the three quarks. That's if they're red, blue, and green. Okay. And then we can do the same. We can do something similar to what we did before, where we construct an amplitude and then we get a color factor and we ask whether that color factor is overall positive or negative. And then we find that it's negative or positive in the case that these are in the color signaling state, and it's negative otherwise. We're not going to have time to go into the details. And trust me, you'd hate them anyway. They would have been insightful. All right, so this is what I'm going to do because we didn't get to cover the weak interactions at all. I'm going to go ahead and post my weak interaction notes with today's lecture. Okay, so the lecture notes that you see posted online will be rather long. So I began by filling out that chart we started last time of the ABC theory, the QED theory, the QCD theory, and then you can already see down to there is the first three interactions, and then the rest of that is the weak. So the weak sucks. And then I take that and I actually look at several very important calculations. So for example, I do in detail the muon lifetime, the neutron decay, and pion decay. Pion decay is interesting for a particular helicity argument. And then I also go into some discussion about the Kavibo-Kobayashi-Moskawa matrix, which rotates the color, or the quark eigenstates. So there's a lot of sort of extra information in here if you want to look at it. The bottom line, though, is that the weak interactions are, at least superficially, much uglier than QCD or QED. But there's a very good reason to anticipate that that would be the case, because the weak interactions at low energies correspond to a spontaneously broken symmetry. I mean, did you see that Higgs Lagrangian? It was nasty after you broke the symmetry. It was fine before you broke it, but it was nasty after you broke it. Well, you were looking at a Higgs Lagrangian for a U1. Imagine what it would look like for SU2 left cross U1 hypercharge. It would be hideous. So the nastiness of the weak interactions, this complicated structure, is entirely tied up with the fact that they're just spontaneously broken. If we could go to high enough energies where that energy is restored, then working with the weak interactions would look a little more akin to working with QCD or QED. We'd still have that funniness of that it's SU2 left cross U1 hypercharge, but whatever. Okay. So to work with the weak interactions brings in a whole host of complications which would occupy us for at least a month if we actually wanted to do some of these calculations. The simplest calculations you can get away with, like muon decay, you can get away with because it's not a strong interaction process, so you don't have a lot of this quark mixing matrix stuff to worry about. For your final exam, which I have to hand out, sorry, I knew there was a reason. For your final exam, you're not going to need any knowledge of the weak interaction. The strong interactions would help out, and that's why I wanted to make sure I got through at least the calculations that we did today, although there's not technically any strong interactions on your final exam. When we come in Thursday, we're going to talk about renormalization, and that will largely be in the context of QED, although we will touch on the quantum chromodynamics case. When I get these out to you, I want you to flip them over and look at the back side. So if you flip them over and look at the back side, there are some comments, and I want to get this established before you leave. This is a final exam. It's not a homework, so I would like for you to work on this on your own when you're not in my presence. When you're in my presence, you can work collaboratively because I can make sure that I don't have people just sitting there copying down something that's on someone else's paper. I would let you work collaboratively outside of my presence if I could be assured that you would, And I don't think any of you would start out doing anything nefarious, but I kind of feel like in the last hour, when you're desperate and you pay attention to everything but my class, you might be tempted to write some stuff down. So those are the rules. You can work on it on your own unless you're in my office hours, in which case you can work with me or with other people. For those office hours, you might note I've been pretty generous. Tomorrow I'm only going to be able to meet from 2 to 3 because I have to go and prepare for something right after. I don't think too many of you are going to get very far on this before tomorrow at 2 o'clock anyway. But this Saturday I will be on campus. The building will be unlocked, so you can come by and talk to me between 3 and 5, and then the same for Monday. However, for Tuesday, I have just, in the last, actually since I printed these, I just on Tuesday had to schedule a meeting from 2 to 4. So what we'll do is we'll start at 4 and go to 7. So scratch out Tuesday 2 to 5 and make that 4 to 7. You guys can keep me here late. Please note this is due Wednesday at 4 and there are no office hours on Wednesday. I'm not going to do that myself. And I'm not going to let you do it to me. So you're going to spend Wednesday writing up your work and you're not going to be doing last minute stuff. Okay. So please, only 3 problems. They're rather long. But get started on it early so you got plenty of opportunities to come in and get help on it.
I'm gonna finish it by tomorrow.
Oh, yeah.
Maybe we should hang out do it during the poster session. Because we're all going to be sitting around for 3 hours.
Whiteboard and just sit there and do it.
Yeah, sorry. Hey, Alex, you'll be at the poster session, right? Can we work on this at the poster session if you're there?
I don't.
No, sorry, we don't want to talk about our project right now.